There is a strange paradox in how we display our most valuable or dangerous items. We place things of immense worth right out in the open, protected by a material that can shatter with a single misplaced strike. Normally, if you want to attach a heavy-duty lock to a container, the engineering is simple. You drill a hole right through the material and bolt the hardware down. But you cannot drill into a tempered glass showcase. The process of tempering creates immense internal tension within the pane. Piercing that surface compromises the entire structure, instantly reducing the glass to thousands of dull pebbles. Instead of drilling, modern locks use high-density nylon pads clamped directly to the glass. This material evenly distributes the compressive force. That distributed pressure generates massive friction, turning a slick surface into an immovable anchor point. Securing these cabinets requires engineers to completely ignore standard vault construction. There is no penetration into the material at all. The entire defense rests on precise, unrelenting friction. The surface of the glass is only half the problem. When you look at sliding showcase doors, the real vulnerability is the tiny, millimeter-wide gap where the two panels overlap. Intruders almost never strike the center of the glass. It's loud, unpredictable, and draws immediate attention. They exploit the geometry of that overlap to simply pry the doors apart or slide them open. To counter this, a sliding ratchet lock is introduced. Rather than biting into the glass, the lock slides a rigid metal bar straight through that gap, paralyzing the lateral movement of the doors. They physically cannot slide past one another. When humans install these friction-based mechanisms, our instincts often take over. We assume that to maximize security, we need to crank the clamp down as tight as physically possible. That is the exact wrong approach. Clamping down too hard creates what engineers call a stress riser, a focal point of extreme microscopic tension. Under a slight temperature shift or a minor bump, that concentrated stress causes the tempered pane to spontaneously explode. Securing a glass display requires a careful balancing act of physics. Hardware that is too loose will slip off, but cranking it too tight creates a condition for self-destruction. Stepping away from the physics of the glass, we have to look at the environment where these cabinets actually live. Busy, fast-paced retail floors, where staff are dealing with constant distractions. Traditional key locks have a glaring vulnerability here. They require a rushed employee to physically insert and turn a key to resecure the merchandise. Often, they simply slide the door shut and walk away. Hardware designers solved this glaring problem with the plunger lock. It secures the track with a single violent push. You only need the key to open the cabinet. Locking it takes zero effort, automating the security process and removing the employee's choice from the equation. But human behavior is only one variable. Cabinets are built with wood or metal frames that swell and contract with seasonal humidity. A rigid metal lock set perfectly to summer dimensions will warp and fail in the winter. To fix this, engineers use a breathing ratchet lock. A toothed bar automatically adjusts its grip to bridge the shifting gap. As the frame swells or shrinks, it accommodates those changes, maintaining a tight perimeter without forcing rigid metal against delicate glass. A reliable perimeter requires hardware engineered to adapt to both environmental chaos and human error. In a high-end gallery or a museum, the entire purpose of a display case is to disappear. A large, obtrusive piece of metal hardware breaks the visual illusion of the exhibit. You will often see these locks finished in matte black or satin nickel. These are not stylistic choices. They are forms of optical engineering. Those specific finishes are mathematically selected to absorb the glare of overhead spotlights. By suppressing light reflection, the hardware forces the human eye to ignore it and focus entirely on the illuminated artifact inside. Even with light-absorbing finishes, there is an assumption that a lock always requires an exposed keyway to function. The magnetic lock removes the keyway entirely. It features zero exterior hardware visible to the naked eye. A specially coated magnetic key is placed directly against the outside of the cabinet. The magnetic force penetrates right through the solid material of the door and pulls the internal levers into alignment, releasing the catch from the inside. In these settings, the hardware performs its mechanical function while remaining effectively invisible to the casual observer. Beyond the gallery floors, glass cabinets are used in environments with strict compliance rules, like hospital pharmacies and research laboratories. Here, the mechanical hardware connects to a hidden digital layer. We move past the physical friction of turning a metal key, replacing it with the invisible millisecond handshake of an RFID card or a Bluetooth signal. The card or signal transmits an encrypted packet to a microcomputer embedded directly into the frame. These smart locks don't just keep people out, they record exactly who gets in. Every interaction creates a permanent digital paper trail. If a technician accesses a controlled cabinet at 3 in the morning, the system logs the user, the timestamp, and flags behavioral anomalies. The glass cabinet evolves from a passive defensive box into an active surveillance node. With a traditional lock, a lost or stolen physical key is a localized catastrophe. You have to physically dispatch a locksmith to drill out the cylinder and replace the hardware before someone empties the shelves. In a networked system, a manager in a centralized command center can instantly revoke access privileges across the entire globe with a single keystroke. That digital command overrides the physical reality of the room. The stolen credential is rendered completely useless before a thief even reaches the glass. Securing a modern display involves a rapid coordination of forces. Cams rotate, nylon pads apply pressure. Magnetic fields bridge barriers, and digital protocols verify access. A simple glass cabinet relies on a hidden network of friction, magnetism, and data. Behind the fragile appearance, these systems maintain a constant, silent defense.